Hello everyone, welcome back. I'm your friend in Sexto. Today, we're going to learn the math section of triangles. Sorry, the right triangles and what is this word?
Right triangles and trigonometry.
Trigonometry. All right, right triangles and trigonometry. Let's get into it.
Pythagorean theorem.
Pythagorean theorem. Pythagorean theorem.
Pythagorean theorem.
Pythagorean theorem. All right. Pythagorean theorem. Let's learn this.
We have an interesting shape right over here. The base is a rectangular prism, and the dimensions of that rectangular prism, it's 3 units, I guess we could say tall, 4 units wide, and then 4 units long. And then on top of that, we have what you could call a right pyramid, where the height of this right pyramid, so if you start at the center of its base right over here, and you go to the top, this height right over here is 1 unit. And this hasn't been drawn completely to scale, and kind of the perspective skews it a little bit. But our goal here is to figure out what is the length of one of these edges right over here. So either that one or this one right over here. What is that length? And we will call that x. And so I encourage you to pause this video and try to think about it on your own. Remember, this is a right pyramid. So what that tells us is that this red line that's a 1 unit long, it is perpendicular to this entire plane. It's perpendicular to the top of the rectangular prism. So with that in mind, I encourage you to pause the video and see if you can figure it out. And I will give you a hint. You will have to use the Pythagorean theorem maybe more than once. All right. So I'm assuming you've at least given it a shot. So let's work through it together. So the key here is to realize, well, okay, this point, this base right over here, this point right over here, it's halfway in this direction and halfway in this direction. So we can figure out, well, this entire length right over here is length 4. So halfway, this is going to be, I'll write it with perspective, that's going to be 2, and that's going to be 2, just like that. And then the other thing we can figure out what this length is going to be, because once again it's halfway in that direction. So if this whole thing is 2, and we see it right over here, this is a rectangular prism, so this length is going to be the same thing as this length. So if this whole thing is 2, then each of these, this is going to be 1, and this is going to be 1 right over there. Well, how does that help us? Well, using that information, we should be able to figure out this length. We should be able to figure out this length. Well, why is this length interesting? Well, if we know that length forms a right triangle. That length and the 1 are the 2 non-hypotenuse sides of a right triangle, and then the x would be the hypotenuse. So we could just apply the Pythagorean theorem. So if we can figure out this, we can figure out x. So let's do one step at a time. How do we figure out, I don't know, let me call this length. How do we figure out length A? Well, let's just take it out and look at it in two dimensions. If we look at it in 2 dimensions, it would look something like this. So that's our length A. We know that this length is half of this side right over here. So that's going to be 1. And actually, let me do it at the same colors. So this right over here is the same thing as this right over here. And it is going to be of length 1. And then this right over here is going to be the same as this right over here, which is going to be of length 2. And so we can just use the Pythagorean theorem here. We know that the hypotenuse squared is going to be equal to 1 squared plus 2 squared. 1 squared plus 2 squared, which of course is equal to 1 plus 4, which is equal to 5. So we could write let me do this in the magenta color. We can write a squared is equal to 5, or we could say that a is equal to the principal root of 5. So this length right over here is the square root of 5, the principal root of 5. And now we can use that information to solve for x. And let's take this right triangle. And it takes a little bit of visualization practice to visualize it, right? But notice this is a right triangle. This height right here of length 1 is perpendicular to this entire plane. So let's see if I can draw it. So we have this side is the square root of 5. And then we have a height. Let me do it. It looks like it's in a, well, let's say we're talking about this height right over here. This height right over here is length 1. So I'll draw that. That is 1. And we are trying to figure out x. We are trying to figure out x in order. We're trying to figure out this x. And once again, we know this is a right triangle. This is a right triangle, so we can apply the Pythagorean theorem again. So we will have x squared is equal to 1 squared, which is just, I'll just write it, 1 squared plus square root of 5 squared plus square root of 5 squared. Well, that gets us x squared is equal to 1 plus 5, right? Square root of 5 squared is just 5. So 1 plus 5 is equal to 6. So we get x is equal to the square root of 6. And we're done. We figured out the length of this side.
So actually what he does, or what he did, is simply applying 2 times of the Pythagorean theory. But how can we prove it? As you can see, here we got 2 kind of proof. Let's get into the first one.
What we're going to do in this video is study a proof of the Pythagorean theorem that was first discovered, or as far as we know, first discovered by James Garfield in 1876. And what's exciting about this is he was not a professional mathematician. You might know James Garfield as the 20th president of the United States. He was elected president. He was elected 4 years after in 1880, and then he became president in 1881. And he did this proof while he was a sitting member of the United States House of Representatives. And what's exciting about that, it shows that Abraham Lincoln was not the only U.S. politician or not the only U.S. president who was really into geometry. And what
So this was interesting. That from this video we could know the U.S. president, the U.S. president could be very good at mathematics, or let's say any subject that's more nearly to the science. But in China, I guess that's a little bit different because, as far as I know, those leaders are generally not good at mathematics. You know, they are good at languages, but they're not good at the science or related subjects.
Garfield realized is if you construct a right triangle, so I'm going to do my best attempt to construct one. So let me construct one right here. So let's say that this side right over here is length B. Let's say this side is length A. And let's say that this side, the hypotenuse of my right triangle, has length C. So I've just constructed a right triangle, and let me make it clear. It is a right triangle. He essentially flipped and rotated this right triangle to construct another one that is congruent to the first one. So let me construct that. So we're going to have length B, and it's collinear with length A. It's along the same line, I should say. They don't overlap with each other. So this is side of length B, and then you have a side of length, let me draw it, this should be a little bit taller, side of length B, and then you have your side of length A at a right angle. Your side of length A comes in at a right angle, and then you have your side of length C. You have your side of length C. So the first thing we need to think about is, what's the angle between these two sides? What's this mystery angle? What's that mystery angle going to be? Well, it looks like something, but let's see if we can prove to ourselves it really is what we think it looks like. If we look at this original triangle and we call this angle theta, what's this angle over here? The angle that's between sides A of length A and length C. What's the measure of this angle going to be? Well, theta plus this angle have to add up to 90 because you add those two together, they add up to 90, and then you have another 90. It's going to get 180 degrees for the interior angles of this triangle. So if these two have to add up to 90, this angle is going to be 90 minus theta. Well, if this triangle up here is congruent, and we've constructed it so it is congruent, the corresponding angle to this one is this angle right over here. So this is also going to be theta, and this right over here is going to be 90 minus theta. So given that this is theta, this is 90 minus theta, what is our angle going to be? Well, they all collectively kind of go 180 degrees. So you have theta plus 90 minus theta plus our mystery angle is going to be equal to 180 degrees. The thetas cancel out, theta minus theta, and you have 90 plus our mystery angle is 180 degrees. Subtract 90 from both sides, and you are left with your mystery angle equaling 90 degrees. So that all worked out well. So let me make that clear. Let me make that clear. And that's going to be useful for us. That's going to be useful for us in a second. It's going to be useful. So we can now say definitively that this is 90 degrees. This is a right angle. Now what we are going to do is we are going to construct a trapezoid. This side A is parallel to side B down here, the way it's been constructed. This is just one side right over here. This goes straight up. And now let's just connect these two sides right over there. Connect these two sides right over there. So there's a couple of ways to think about the area of this trapezoid. One is we could just think of it as a trapezoid and come up with its area, and then we could think about it as the sum of the areas of its components. So let's just think of it as a trapezoid. So what do we know about the area of a trapezoid? Well, the area of a trapezoid is going to be the height of the trapezoid, which is A plus B. A plus B. That's the height of the trapezoid, times, the way I think of it, the mean of the top and the bottom, or the average of the top and the bottom. So this times 1/2 times A plus B. A plus B. A plus B. And the intuition there, you're taking the height times the average of this bottom and the top. The average of the bottom and the top gives you the area of the trapezoid. Now, how can we also figure out the area with its component parts? So this should be, regardless of how we calculate the area, as long as we do correct things, we should come up with the same result. So how else can we come up with this area? Well, we could say it's the area of the two right triangles. The area of each of them is 1/2 A times B. 1/2 A times B. But there's two of them. Let me do that B in that same blue color. But there's two of these right triangles, so let's multiply by 2. So this 2 times 1/2 AB, that takes into consideration this bottom right triangle and this top one. And what's the area of this large one that I will color in green? What's the area of this large one? Well, that's pretty straightforward. It's just 1/2 C times C. So plus 1/2 C times C, which is 1/2 C squared. Now let's simplify this thing and see what we come up with. And you might guess where all of this is going. So let's see what we get. So we can rearrange this. So this is 1/2. Let me rearrange this. So it's 1/2 times A plus B squared. A plus B squared is going to be equal to 2 times 1/2. Well, that's just going to be 1. So it's going to be equal to A times B plus 1/2 C squared. Plus 1/2 C squared. Well, I don't like these 1/2s laying around, so let's multiply both sides of this equation by 2. I'm just going to multiply both sides of this equation by 2. On the left-hand side, I'm just left with A plus B squared. So let me write that. A plus B squared plus B squared. And on the right-hand side, I am left with 2AB b, trying to keep the color coding right. And then 2 times 1/2 c squared, that's just going to be c squared plus c squared. Well, what happens if you multiply out a plus b times a plus b? What is a plus b squared? Well, it's going to be a squared plus 2ab plus 2ab plus b squared. And then our right-hand side is still, it's going to be equal to all of this business. And changing all of the colors is difficult for me. So let me copy and let me paste it. So it's still going to be equal to the right-hand side. Well, this is interesting. How can we simplify this? Is there anything that we can subtract from both sides? Well, sure there is. You have a 2ab on the left-hand side. You have a 2ab on the right-hand side. Let's subtract 2ab from both sides. If you subtract 2ab from both sides, what are you left with? You are left with the Pythagorean theorem. So you're left with a squared plus b squared is equal to c squared. Very, very exciting. And for that, we have to thank the 20th President of the United States, James Garfield. And I really, this is really exciting because the Pythagorean theorem was around for thousands of years before James Garfield, and he was able to contribute just kind of fiddling around while he was a member of the U.S. House of Representatives.
It's just great for this United States because he, instead of leading the whole country, or as he said, he's just a representation of the United States people, but he's also able to do some contributions to the mathematics world. That was great. That's kind of improve that his intelligence. Special right triangles. Right, let's get into it.
What I want to do in this video is discuss a special class of triangles called 30, 60, 90 triangles. And I think you know why they're called this. The measures of its angles are 30 degrees, 60 degrees, and 90 degrees. And what we're going to prove in this video, and this tends to be a very useful result, at least for a lot of what you see in a geometry class and then later on in a trigonometry class, is the ratios between the sides of a 30, 60, 90 triangle. That if the hypotenuse has length x, so that's, remember, the hypotenuse is opposite the 90-degree side. If the hypotenuse has length x, what we're going to prove is that the shortest side, which is opposite the 30-degree side, has length x over 2, and that the 60-degree side, or the side that's opposite the 60-degree angle, I should say, is going to be square root of 3 times the shortest side. So square root of 3 times x over 2. That's going to be its length. So that's what we're going to prove in this video. And then in other videos, we're going to apply this. We're going to show this is actually a pretty useful result. Now let's start with a triangle that we're very familiar with. So let me draw ourselves an equilateral triangle. So drawing the triangles is always the hard part. So this is my best shot at an equilateral triangle. And let's call this A, B, C. I'm just going to assume that I've constructed an equilateral triangle. So triangle ABC is equilateral. And if it's equilateral, that means all of its sides are equal. And let's say that it has length, and let's say equilateral with sides of length x. So this is going to be x, this is going to be x, and this is going to be x. We also know, based on what we've seen from equilateral triangles before, that all the measures of all of these angles are going to be 60 degrees. So this is going to be 60 degrees, this is going to be 60 degrees, and then this is going to be 60 degrees. Now what I'm going to do is I'm going to drop an altitude from this top point right over here. So I'm going to drop an altitude right down, and by definition, when I'm constructing an altitude, it's going to intersect the base right here at a right angle. So that's going to be a right angle, and then this is going to be a right angle. And it's a pretty straightforward proof to show that this is not only is this an altitude, not only is it perpendicular to this base, but it's a pretty straightforward proof to show that it bisects the base. And you could pause it if you like and prove it yourself. But it really comes out of the fact that it's easy to prove that these two triangles are congruent. So let me prove it for you. So let's call this point D right over here. So triangles ABD and BDC, They clearly both share this side. So this side is common to both of them right over here. And then we could do whatever that we have. This angle right over here is congruent to this angle over there. This angle right over here is congruent to this angle over here. And so if these two are congruent to each other, then the third angle has to be congruent to each other. So this angle right over here needs to be congruent to that angle right over there. So these two are congruent. And so you can use actually a variety of our congruence postulates. We could say side angle side angle side congruence. We could use angle side angle. Any of those to show that triangle ABD is congruent to triangle CBD. And what that does for us, and we could use, as I said, we could use angle side angle or side angle side, whatever we like to use for this. What that does for us is it tells us that the corresponding sides of these triangles are going to be equal. In particular, the length of, AD is going to be equal to CD. AD is going to be equal to CD. These are corresponding sides. So these are going to be equal to each other. And if we know that they're equal to each other and they add up to x, remember this was an equilateral triangle of length x, we know that this side right over here is going to be x over 2. We know this is going to be x over 2. Not only do we know that, but we also knew when we dropped this altitude, we showed that this angle has to be congruent to that angle, and their measures have to add up to 60. So if two things are the same and they add up to 60, this is going to be a 30 degrees, and this is going to be 30 degrees. So we've already shown one of the interesting parts of a 30, 60, 90 triangle, that if the hypotenuse, notice, and I guess I didn't point this out, by dropping this altitude, I've essentially split this equilateral triangle into two 30, 60, 90 triangles, 30, 60, 90 triangles. And so we've already shown that if the side opposite the 90 degree side is x, that the side opposite the 30 degree side is going to be x over 2. That's what we showed right over here. Now we just have to come up with the third side, the side that is opposite the 60 degree side. The side that is opposite the 60 degree side right over there. And let's call that length, well, I'll just use the letters that we already have here. This is BD. And we can just use a Pythagorean theorem right here. BD squared plus this length right over here squared plus x over 2 squared is going to be equal to the hypotenuse squared. So we get BD squared plus x over 2 squared. This is just straight out of the Pythagorean theorem. Plus x over 2 squared is going to equal this hypotenuse squared. Is going to equal x squared. And just to be clear, I'm looking at this triangle right here. I'm looking at this triangle right over here on the right, and I'm just applying the Pythagorean theorem. This side squared plus this side squared is going to equal the hypotenuse squared. And let's solve now for BD. You get BD squared plus x squared over 4. X squared over 4 is equal to x squared. You could view this as 4x squared over 4. That's the same thing, obviously, as x squared. And then if you subtract 1/4 x squared from both sides, or x squared over 4 from both sides, you get BD squared is equal to 4x squared over 4 minus x squared over 4 is going to be 3x squared over 4. So it's going to be 3x squared over 4. Take the principal root of both sides. You get BD is equal to the square root of 3 times x. Principal root of 3 is square root of 3. Principal root of x squared is just x over the principal root of 4, which is 2.
Alright, so for this video that we have known, okay, let's say from this video we have learned out that the theorem 30, 40, 90 degrees triangles theorem is come out from a very basic idea of the let's say how they call that, equilateral triangle. I guess that's that, but alright, I'll just do some search for it.
Equilateral triangle.
Okay, here we go. They call that kind of triangle
Equilateral triangle.
Equilateral triangle. Right. So the idea of this theorem has come out from the equilateral triangle. all you have to do is to split the equilateral triangle into two equal part of triangles. Then you could get that result or get that principle or rules out from the
Pythagorean theorem.
out of the Pythagorean theorem. So it's just of like, building a program. If you need to solve a big problem, you just have to solve a lot of different sub-problems. Then based on those sub-problem solutions, you construct the big solution. But as you know, in China, they would just like to let you memorize the general rules without telling you why it comes out or how he think out about those solutions. They will never tell you that, which will lead to an result that is you'll never ever be able to find a new solution by yourself because you don't know how others found out a solution in the history.
Introduction to the trigonometric ratios.
Introduction to the trigonometric ratios. What is that?
We've got two right triangles here. Let's say we also know that they both have an angle whose measure is equal to theta. So angle A is congruent to angle D. What do we now know about these two triangles? Well, for any triangle, if you know two of the angles, you're going to know the third angle because the sum of the angles of a triangle add up to 180 degrees. So if you have two angles in common, that means you're going to have three angles in common. And if you have three angles in common, you are dealing with similar triangles. Let me make that a little bit clearer. So if this angle is theta, this is 90. They all have to add up to 180 degrees. That means that this angle plus this angle up here have to add up to 90. We've already used up 90 right over here. So this angle A and angle B need to be complements. So this angle right over here needs to be 90 minus theta. Well, we can use the same logic over here. We already used up 90 degrees over here. So we have a remaining 90 degrees between theta and that angle. So this angle is going to be 90 degrees minus theta. 90 degrees minus theta. You have three corresponding angles being congruent. You are dealing with similar triangles. Now, why is that interesting? Well, we know from geometry that the ratio of corresponding sides of similar triangles are always going to be the same. So let's explore the corresponding sides here. Well, the side that jumps out when you're dealing with right triangles the most is always the hypotenuse. So this right over here is the hypotenuse. This hypotenuse is going to correspond to this hypotenuse right over here.
All right, from here we know that we get a new word called hypotenuse. Hypotenuse. Well, it's just a representation for this side. If you have a right triangle, it's the side that's opposite to the right triangle, something like that.
And we could write that down. This is the hypotenuse of this triangle. This is the hypotenuse. This is the hypotenuse of that triangle. Now, this side right over here, side BC, what side does that correspond to? Well, if you look at this triangle, you can kind of view it as the side that is opposite this angle theta. So it's opposite. If you go across the triangle, you get there. So let's go opposite angle D. If you go opposite angle A, you get to BC. Opposite angle D, you get to EF. You get EF. So it corresponds to this side right over here. And then finally, side AC is the one remaining one. We could view it as, well, there's two sides that make up this angle A. One of them is a hypotenuse. We could call this maybe the adjacent side to it. And so D corresponds to A. And so this would be the side that corresponds. Now, the whole reason I did that is to leverage that corresponding sides, the ratio between corresponding sides of similar triangles is always going to be the same. So, for example, the ratio between BC and the hypotenuse, BA. So let me write that down. BC over BA is going to be equal to EF over ED. EF EF, the length of segment EF, over the length of segment ED, over the length of segment ED. Or we could also write that the length of segment AC, so AC over the hypotenuse, over this triangle's hypotenuse, over AB, is equal to DF over DE. Once again, this green side over the orange side. These are similar triangles. They're corresponding to each other. So this is equal to DF over DE over DE.
Well, from this graph, we know nothing because as far as I know, this property was not only it can so instead of using this property for the right triangle, you can also use it for any triangles that with the similarity property as the base. So in other words, if two triangles are similar,
or we could also,
if two triangles are similar, then in other words, the ratio between each of their corresponding side is always the same.
Also saying we could keep going, but I'll just do another one. Or we could say that the ratio of this side right over this.
Okay, that was boring. Let me say what we can get from the. Okay, I guess the most important one is for you to understand the sine and cosine kind of concepts.
We see in a triangle, or I guess we know in a triangle, there's three angles. And if we're talking about a right triangle, like the one that I've drawn here, one of them is going to be a right angle. And so we have two other angles to deal with. And what I want to explore in this video is the relationship between the sine of one of these angles and the cosine of the other, the cosine of one of these angles and the sine of the other. So to do that, let's just say that this angle, I guess we could call it angle A, let's say it's equal to theta. If this is equal to theta, if its measure is equal to theta degrees, say, what is the measure of angle B going to be? Well, the thing that will jump out at you, and we've looked at this in other problems, is the sum of the angles of a triangle are going to be 180 degrees, and this one right over here, it's a right triangle. So this right angle takes up 90 of those 180 degrees, so you have 90 degrees left. So these two are going to have to add up to 90 degrees. This one and this one, angle A and angle B, are going to be complements of each other. They're going to be complementary. Or another way of thinking about it is B could be written as 90 minus theta. If you add theta to 90 minus theta, you're going to get, or theta to 90 degrees minus theta, you're going to get 90 degrees. Now, why is this interesting? Well, let's think about what the sine of theta is equal to. Sine is opposite over hypotenuse. The opposite side is BC. So this is going to be the length of BC over the hypotenuse. The hypotenuse is side AB. So the length of BC over the length of AB. Over the length of AB. Now, what is that ratio if we were to look at this angle right over here? Well, for angle B, BC is the adjacent side, and AB is the hypotenuse. From angle B's perspective, this is the adjacent over the hypotenuse. Now, what trig ratio is adjacent over hypotenuse? Well, that's cosine. So, ka-toa. Let me write that down. Sine doesn't hurt. Sine is opposite over hypotenuse. We see that right over there. Cosine is adjacent over hypotenuse. Ka. And toa, tangent, is opposite over adjacent. So from this angle's perspective, taking the length of BC, which is BC is its adjacent side, and the hypotenuse is still AB. So from this angle's perspective, this is adjacent over hypotenuse. Or another way of thinking about it, it's the cosine of this angle. So that's going to be equal to the cosine of 90 degrees minus theta. That's a pretty neat relationship. The sine of an angle is equal to the cosine of its complement. So one way to think about it, the sine of, we could just pick any arbitrary angle. Let's say the sine of 60 degrees is going to be equal to the cosine of what? And I encourage you to pause the video and think about it. Well, it's going to be the cosine of 90 minus 60. It's going to be the cosine of 30 degrees. 30 plus 60 is 90. And of course, you could go the other way around. We could think about the cosine of theta. The cosine of theta is going to be equal to the adjacent side to theta, to angle A, I should say. And so the adjacent side is right over here. That's AC. So it's going to be AC over the hypotenuse, adjacent over hypotenuse. The hypotenuse is AB. But what is this ratio from angle B's point of view? Well, the sine of angle B is going to be its opposite side, AC over the hypotenuse, AB. So this right over here, from angle B's perspective, this is angle B's sine. So this is equal to the sine of 90 degrees minus theta. So the cosine of an angle is equal to the sine of its complement. The sine of an angle is equal to the cosine of its complement.
That makes sense because before this video, he never tell us what is a sine and what is a cosine. Yeah, I'm pretty sure about that.
Let's just do a ton of more examples.
Okay, here we go. Here we got it. That's a concept. It should be right out somewhere. Ratios in right triangles. All right.
So we've been given some information about these. Then they say use one of the triangles, so use one of these three triangles to approximate the ratio. The ratio is the length of segment PN divided by the length of segment.
Okay, that was not right. Let me do this. Sine and cosine in right triangle. Then by doing this search, it will lead us into a page or a website called Math is Fun. This website is good because it has a lot of basic concept about some mathematical terminology. And you can get into it and learn those concepts. Because for example, now, as you could know from this graph or this page, we could easily get the idea of what is sine, what is cosine, and what is tangent kind of thing. You could get the concepts very intuitively. And for now, I guess this is just a definition for the symbol sine or cosine or tangent. There has no, let's say, there has no magic out of it. It's just a definition. And for a definition, what you need to do is to memorize it. That's all. Let's in the end watch one more video.
A tiny but horrible alien is standing at the top of the Eiffel Tower. So this is where the tiny but horrible alien is, which is 324 meters tall, and they label that the height of the Eiffel Tower, and threatening to destroy the city of Paris. A men in black, or I guess a men in black agent, I was about to say maybe it should be a man in black. A men in black agent is standing at ground level, 54 meters across the Eiffel Square. So 54 meters from, I guess you could say, the center of the base of the Eiffel Tower, aiming his laser gun at the alien. So this is him aiming the laser gun. At what angle should the agent shoot his laser gun? Round your answer, if necessary, to 2 decimal places. So if we construct a right triangle here, and we can, so the height of this right triangle is 324 meters. This width right over here is 54 meters. It is a right triangle. What they're really asking us is, what is the angle? What is this angle? What is this angle right over here? And they've given us 2 pieces of information. They gave us the side that is opposite the angle, and they've given us the side that is adjacent to the angle. So what trig function deals with opposite and adjacent? And to remind ourselves, we can write, like I always like to do, SOHCAHTOA. And these are really by definition, so you just kind of have to know this, and SOHCAHTOA helps us. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So we can say that the tangent, we can write that the tangent of theta is equal to the length of the opposite side, 324 meters over the length of the adjacent side, over 54 meters. Now you might say, well, okay, that's fine. No, so what angle gives when I take its tangent gives me 324 over 54? Well, for this, it will probably be useful to use a calculator. And the way that we'd use a calculator is we would use the inverse tan function. So we could rewrite this as we're going to take the inverse tangent, and sometimes it's written as tangent, kind of with this -1 superscript. So the inverse tangent of tan of theta is going to be equal to the inverse tangent of 324 over 54. And just to be clear, what is this inverse tangent? This just literally says, this will return what is the angle that when I take the tangent of it gives me 324 over 54. This says, what is the angle that when I take the tangent of it gives me tangent of theta. So this right over here is this just simplifies to theta. Theta is the angle that when you get the tangent of it gets you tangent of theta. And so we get theta is equal to inverse tangent of 324 over 54. Once again, this inverse tangent thing you might find confusing, but all this is saying is, over here we're saying tangent of some angle is 324 over 54. This is just saying is my angle is whatever angle I need so that when I take the tangent of it, I get 324 over 54. It's how we will solve for theta. So let's get our calculator out, and let's say that we want our answer in degrees. And actually they should, well, I'm just going to assume that they want our answer in degrees. So let me make sure my calculator is actually in degree mode. So I'll go to the second mode right over here, and actually it's in radian mode right now. So let me make sure I'm in degree mode to get my answer in degrees. Now let me exit out of here, and let me just type in the inverse tangent. So it's in this yellow color right here. Inverse divided by 54 is going to be 80 and they told us to round to 2 decimal places, 80.54 degrees. So theta is equal to 80.54 degrees. That's the angle at which you should shoot the gun to help defeat this horrible alien.
So from this video, at least we could know the right triangle ratio kind of concept as used to calculate the degree for some problems, and that's a real use case for that theory. Okay, I guess this is today's video, and inside of this video we have learned about the concept about the right triangle and what is sine and what is cosine and so kind of things like that. Okay, I will see you guys in the next video. Bye.